This video is on chapter 23, and in particular example 165. The solution to example is 165 is the only thing in this chapter that is not in your notes. So I will go through this proof in the video. So we want to prove that this sequence converges. We're going to use theorem 161, which says every bounded monotonic sequence converges. And so the first thing we want to do is note that this sequence actually is increasing. So note that the sequence k equal 1 to n, 1 over k factorial, n equal 1 to infinity, which is equal to what? The first term of our sequence when n is 1 is 1. When n is equal to 2, then the second term of the sequence is 1 plus 1 over 2 factorial, which is 1 plus 1/2. The third term of our sequence is 1 plus 1/2 plus 1 over 3 factorial. And you see that every term of the sequence is the previous term plus 1 over k factorial, whatever, or 1 over n factorial, whatever n happens to be. So we can tell just by looking at the sequence that it is increasing. So note that this sequence is increasing. So what we need to do now is prove that it's monotonic. So it remains to show that the sequence is increasing, is bounded above. Sorry. So we've shown that it's increasing, so it's monotonic. So now we need to show that it's bounded above. And we're going to use previous examples to do that. There's another sequence we looked at before spring break that we saw was bounded above by 2. So we're going to prove that this sequence is bounded above by 2 by comparing it to that one. Okay, so for each natural number n, so for each n in n, let's set S sub n to be the sum I equals 0 to n of 1 over 2 to the I, and T sub n just going to be the terms of our sequence. So T sub n is going to be the sum from k equal 1 to n of 1 over k factorial. And our claim is that for n greater than or equal to 4, T sub n is strictly less than S sub n. So now in the middle of the proof of our example, we're going to prove our claim. And we're going to prove our claim using induction. So first, note that S sub 4 is equal to 31 divided by 16, almost 2. T sub 4 is equal to 41 divided by 24 not as close to 2. And you can calculate those as decimals if you want to. S sub 4 is 1.9375, and T sub 4 is 1.708, repeating 3's, if you're interested in what those are as decimals. So, the claim is true for and equal to 4. So that's the basis step. So now we want to do the inductive step. So now suppose that L is a natural number and T sub L is strictly less than S sub L. Then what does this mean? Well, we start with our T sub L is strictly less than S sub L. And now we'll add something on the left, T sub L plus 1 over L plus 1 factorial. And on the right, we'll add something smaller. I'm sorry, we will add something larger, so that the left side is less than the right side. And how do we know that 1 over L plus 1 factorial is smaller than 1 over 2 to the L plus 1? We've already proven that. That's example 133. Okay, and what is T sub L plus 1 over L plus 1 factorial? That's T sub L plus 1. What is S sub L plus 1 over 2 to the L plus 1? That's S sub L plus 1. So that is the inductive step. So the claim is proved by the principle of mathematical induction. And our proof, put a claim there. We've only proved the claim. We haven't proved the example yet, but we are close. Okay, now we have previously seen that our sequence of the S sub n's is bounded above by 2. Since this sequence, the sum I equals 0 to n of 1 over 2 to the I, n equal 1 to infinity, is bounded above by 2, the sequence that we're interested in, the sum of k equal 1 to n of 1 over k factorial, n equal 1 to infinity, is also bounded above by 2. Therefore, the sequence converges by theorem 161. And that concludes the proof of example 165. Everything else in this chapter you already have in your notes.